Here's our setup. We have city A and city B, and we're trying to find the fastest possible way to go from A to B. The obvious approach would be to take a straight line path, but let's introduce a twist. There's a faster region above where the speed is 3 times more than the bottom region. Now there's probably a better route we can take where we go up from city A, travel quickly across the highway, and get back to city B. We could take a curved path like this within the highway region, but that would actually increase the travel time. A straight segment that just touches the highway is enough and more efficient. By the end of the video, we'll show how soap films help find the minimum time path. Let's simplify the problem for now. Suppose the whole terrain is uniform. If you pick any arbitrary curved path between A and B, your intuition probably tells you that the shortest path is a straight line. We can mathematically prove this using calculus of variation and the Euler-Lagrange equation. If you're interested, feel free to read through the document in the description. For the purpose of the video, we are going to instead let nature solve it using soap films. Soap films have a fascinating property that they always minimize their surface area. We can harness this by creating setups with different configurations with any number of pins and any arrangement representing the optimization problem we want to solve, and let nature do the rest. The film stretches between pins in a network and naturally minimizes the total area. In the previous subproblem, we were basically minimizing the distance, and therefore we were able to represent it as a soap setup to compute it. But instead, let's say we have A and B in two different regions with different velocities, or in the language of optics, different refractive indices. How do we model this as a soap setup in this case? Take the setup we had before and see what happens when there's a step change in height. We observe that it's no longer a straight rectangle, now it bends at the step. This is because the film can afford to take a longer path through the lower height region where it contributes less to the total area. If you've guessed that the angles follow Snell's law, then you're correct. In the case of light, let this be d1 and this be d2, and their corresponding velocities be v1 and v2. Then the total time would be d1 by v1 plus d2 by v2. And similarly, the total area of soap film is d1 multiplied by h1 plus d2 times h2. We observe that the height here is analogous to the inverse of velocity or refractive index in optics. In optics, time is minimized when it satisfies Snell's law, and similarly with soap film, it minimizes with the modified Snell's law when we replace refractive index with height. Now let's bring both the points to the same region. This turns into our original problem where we had two cities and a faster region on top, and we're required to find the fastest time path. We can model this as a problem in optics where the top region has a refractive index of 1/3 of the bottom one. Just like we've seen before in the soap setup, this means that the top region has a height of 1/3 than the rest. Pin cities A and B in the lower layer, dip it in soap, and just like that, nature solves our optimization problem. Now let's talk about the angles formed. Observe that for a path like this passing through the middle, it's not efficient. We can optimize reaching that point. There's a sweet spot right over here. Notice that the angle of refraction is 90 degrees, and we can apply Snell's law to find the critical angle. You'll find that the two angles are equal and given by this expression, where VA and VB are the speeds in the faster and slower region. It's not always the case that it has to use a highway to minimize the time. Observe that sometimes the direct blue path is minimum and hence better than the green one. In such a case, the soap film would form directly connecting the pins and not the detour. I'll leave one problem as an exercise. Fixing one of the points, find the locus of the second point where the green detour path is better than the direct blue path. What you'll find is that it's a conic.